Welcome to this session, which is on sequential circuits. But this time we'll be looking at registers and counters. Very complex circuits normally rely on the use of sequential circuits. Such circuits will need memory, and hence the need for registers. These registers are made by combining a number of flip-flops together. So registers are simply putting these flip-flops together, combining them together to give you what? Remember, a flip-flop gives you just one bit. So you put a number of them together, you get a register. So you should be able to explain the operation of registers, explain the operation of shift registers and how to build them, explain the operation of binary counters, and show how to build them using flip-flops and gates, and analyze the operation. So these are the things I expect you to know by the time you finish studying this session. So we'll have an introduction to registers, data formats and classification of registers, shift registers, and then counters. Chapter 12 of the recommended test, Fundamentals of Logic Design, is where you get the basic information on this topic. A flip-flop is a 1-bit memory cell which can be used for storing the digital data. To increase the storage capacity in terms of a number of bits, we have to group a number of flip-flops. Such a group of flip-flops is known as a register. An n-bit register would consist of n number of flip-flops, and it is capable of storing an n-bit word. The binary data in a register can be moved within the register from one flip-flop to the other. In other words, it can be shifted from one flip-flop to the next. The registers that allow such data transfers, we call them shift registers. So those registers that allow us to move data from one register, one flip-flop to the other one, are called what? Shift registers. There are 4 modes of operation of these registers. Yeah, there are 4 fundamental modes of operation of these registers, which you need to understand. You have the serial input and serial output. So serial input, serial output. You have serial input, parallel output. You have parallel input, serial output. You have parallel output, input, and parallel output. And we'll look at each of these. You will have to look at each of these. So this is a 4-bit serial in to serial out shift register. So it's 4 bits. It's got 4 flip-flops, F0, F1, F2, F3. It's only got 1 input and it's got what? 1 output. The data is shifted serially in and out of the register, 1 bit at a time, in either a left or right direction under the control of a clock. So if you let all the flip-flops initially be set at a condition where Q equals Q3 equals to Q2 equals to Q1 equals to Q0 equals to 0, if an entry of a 4-bit binary number is made, let's say 1111, is applied, then this is what you have. F3 at the first clock will become the input, the D input of F3, that is D3, will be connected to what? The D input of Q2, of D2, right? And so on and so forth. So before application of the signal, let Q03, Q2, Q1, Q0 be equal to 0, 0, 0, and apply the least significant bit of the number to be entered. So the least significant bit you apply first. So D in, right? So D in equals to D3. Before the application, so you have SSS0. If you apply on the falling edge of the signal, then F3 will be set and stored in the word register. So then you have 1, 0, 0, 0, because you had applied the first one. And then at the next shift, then F2 now also becomes 1 because the output of 3 is shifted. So you then get that. And then when you apply a signal again, then you get that because it's being shifted. And then when you apply a signal again, you get that. So now you then have Q, all the Qs now have 111 are their outputs. So this table sort of gives you shows you how the data travels within these shift registers. Now we can represent the same information using waveform that we mentioned earlier, right? So this is a stored word. When you apply the data at first, what is stored, then when you apply it again, what you get, when you apply the next clock, and so on. Now, you can have a 4-bit serial input, parallel output, right? In such types of, the data is entered serially, but it's taken out what? In parallel fashion, right? Data is loaded bit by bit. The outputs are disabled as long as the data is loading. So whilst the data is loading, the output is not enabled. As soon as the data loading gets completed, all the flip-flops contain their required data. The outputs are enabled so that all the loaded data is made available. You need 4 cycles are required to load a 4-bit word, hence the need of a simple, hence the speed of operation of a simple is the same as that of what? A SISO. So, because you need 4 cycles, to operate them. So now what you see here is that, yes, you have the input here, the data in onto D3, but then you tap this out. And that is also fed into D2. And again, this is tapped out. The output is tapped out, and so on and so forth. So these are the parallel outputs on this end. So we can also have a parallel input and a serial output. So you input the data parallelly, but you take it out in a serial mode. So if you input a binary word, say B0, B1, B2, B3, if you apply that through a combinational circuit, you apply that through a combinational circuit, this thing can work in either a shift mode or a load mode. So if you say, you can think about it in the load mode, what would happen, and then in the shift mode, what happens. So you can use the shift. You can either say you are shifting or you are doing a load, and you control that through the signal that is shown here, right? So if the bar is below 0, the AND gates 1, 2, 4, and 6. 1, gate 2, 4, and 6, right? They will become active, because of this signal that is coming here. So it depends on what you are activating. Okay, so 2, 4, and 6 will become active. So you know that you're in the load mode. And then when you're in the shift mode, then 1, 3, and 5 becomes active. So that enables the listener to shift through. So take your time, look in the textbook, take your time and read through this and see how it actually operates. So there's a parallel input, serial output. So you have a shift mode and a load mode. One mode in which to actually load the data, and then another mode in which shift the data. I mean, of course, that makes this, because if you're putting the thing in parallelly, in a parallel mode, well, then you must first load it. And then once you've loaded, then you can think about shifting this out. And then the parallel input, parallel output. In this case, you load the data in a parallel fashion, and you take out the data in a parallel fashion as well. So the loaded bits will appear simultaneously at the output. Only the clock pulse is essential, so you only need a clock to either load and then the data. You are not shifting in this case, you are just loading. So there's no shifting. So if you look at the circuit carefully, you don't actually see Q3 being connected to D2 as in previous cases. So we've seen the shift registers, serial input, serial output, serial input, parallel output, parallel input, serial output, and parallel input and parallel output. Now let's look at counters. A counter it's a circuit that is used for counting pulses. Circuits for counting events are frequently used in computers and other digital systems. A counter is a widest application of a flip-flop. So the most commonly used form of a flip-flop is in counting. It's a group of flip-flops which with a clock signal applied. So a group of flip-flops with a clock signal that is applied and goes through them one state after the other. Since a counter circuit must remember its past states, it has to possess memory. The number of flip-flops used will determine how they are connected. Counters can be classified into two broad categories according to the way they are clocked. You can either have synchronous ones or asynchronous ones. A logic diagram for a counter is shown. The T is for toggle. You can either use the J, K flip-flops for this, the J and K flip-flop for this. You can apply an external clock to it, to the counter. So you can see how this is done. So you have a logic one being applied, and then the outputs are connected. So you move from one state to the other. So there's one flip-flop to another flip-flop. In this case, you can count up to what? 4, because you have 4 states altogether. So these are initial states, so first, second, third, and then fourth. So the decimal outputs are shown. So there are 4 different states, and the decimal outputs that you can have. So initially, let's say that all the 2 flip-flops, right, are in the reset state. That's S equals, Q, QA, QB are all zeros. So after the first negative clock edge, as soon as the first negative clock edge is applied, the first flip-flop A will be toggled and QA will be equal to 1. Yeah. After the first is in, this will turn into 1. Will be equal to 1. QA is connected to the clock input of F2, if you look back at the diagram, at the clock input of F2. And since QA has changed from 0 to 1, it is treated as a positive clock of F2. There will be no change to QB, yeah, because that's a negative edge, all right? So you have a QA, QA becomes 0 and 1. So the state then will be what after the first clock. And then at the next state, on the arrival of the second one, the A toggles to 0, so QA is 0, and this acts as a negative edge clock to FB, so it will also toggle, and QB will now be 1. So this is why you have this here, QB will now be 1. So QB, QA will be equal to now what? 1, 0 after the second clock. At the third clock, right, on arrival of the third clock, FA will toggle back to 1, yeah, and QA becomes 1. So that's why you then have QB, QA, all both of them being 1. But QB will not change. If you go back to the distance, it will not change. So it continues to 1. So QB, QA becomes 1, 1. That way you go through all the states, and of course at the next listen, at the fourth negative clock edge, both of them will toggle back to 1, and you'd have gone through the cycle. So this is how accounting is then done, basically. So you look at what happens when, so basically you are looking at this, what happens when you clock that, what happens to the output of this and that, because this acts as a clock to that. And so whatever is happening here will affect this. Now, in a synchronous clock, synchronous counters, let's look at a 2-bit synchronous counter. So here you have JA and KA, yeah, as are the inputs of the flip-flop A. so are tied to logic 1. So they have a logic 1. So the FA would work as a toggle flip-flop. JB and KB inputs are also connected. JB and KB inputs are connected to QA. Now, if clock pulses are applied to all the flip-flops in a counter simultaneously, then such a counter is called synchronous because they are being applied at the same time as opposed to being applied at different times. The important advantage of synchronous clock is that there is no cumulative time delay. So there won't be any time delays here because the things are all applied at the same time. Now let's look at what happens for a 2-bit synchronous up counter. Initially, let both flip-flops be in the reset state. So that is QB, QA are all initially 0. So after the first negative clock, as soon as the first negative edge is applied, FA will toggle to QA and QA will change from 0 to 1. But at the same instant of application of the negative clock edge, QA, JB, which is equal to KB, will be 0. Hence, B, the second flip-flop, will not change its state. So QB will remain 0. So then you will have QB, QA becomes 0, 1 after the first clock pulse. After the second after the second edge, what you have then is that QB will toggle to what? Both of them will toggle. So with QB becoming 1 and the QA changing to 0. At the third negative edge, QB will remain, and then QA will change. And then at the fourth one, they will both change to 0s. So you'd have again gone through the 4 states, of the counter, the counting process. So this is for what? A 2-bit, You can think of this again, you can design this for a 3-bit, So instead of having 2 flip-flops, you have 3 flip-flops. And the same principle would apply. These counters can be classified according to the way they go. So you can have an up or down counters or both up and down counters. So the counters that can either go up or the ones that can go down or the ones that can go up and down. So it's good to take note of that. An up counter and a down counter is combined together to give you an up and down counter. In this case, you have a control input or mode, to determine whether it's going up or down. You will need a combinational circuit to be designed and used between each pair of flip-flops to achieve the up and down operation. So to get the up and down operation, a combinational circuit is what you require to control that form of operation. We also have ripple counters. In the up and down ripple counter, all the flip-flops operate in the toggle mode. So either T flip-flop or J flip-flop can be used. The least significant bit receives the clock directly, but the clock to every other flip-flop is obtained from the Q naught or the Q bar output of the previous one. So the output of the preceding flip-flop is connected to the clock of the next stage if counting is to be achieved. For this mode, the mode select input is a logic 0. And then for the down one, if M equals 1, then the Q bar output of the preceding flip-flop is connected to the next flip-flop. This will operate the counter in the counting mode, as well. So that is how it works. But again, the details of this you find in the textbook, which you can consult to see exactly precisely how it is done. So, question for you to consider is, explain the operation of the shift registers, show how to build them using flip-flops, and analyze their operation. Construct a timing diagram for a shift register, explain the operation of the binary counters, show how to build them using flip-flops and gates, and analyze their operation. So these are sample questions as to how you may be tested on this. Thank you.